Very good morning. Today we are going to see little ahead of our course. So this is lecture 4. We will be still continuing the compound rotations. However, this compound rotation will give an idea why we are using transformation method, or you can say transformation matrix based method in serial manipulator. How further you can say representations all coming, why those representations all coming. These all the aspect we are going to see. So as I already told, we are going to see the continuation of the earlier course. So we'll go back in that sense. So this is as same, you can say, disclaimer. So we'll go as per the same aspect. So we'll be talking about the compound you can say rotations. So the compound rotations will have three things. Okay, we were actually like talking about why pre-multiplication and post-multiplication, and we have seen actually like four general form of using composite rotation or compound rotations. One is actually like the popular one we call global XYZ fixed angle, which is we simply call RPY, roll pitch angle or Winkle angle. So the other one we are going to call Euler angle in general. In that one of the specific we are going to see is ZYX, which is we call Cardan or Bryant angle. So this is what the major aspect. So in this class we will be seeing why pre-multiplication and post-multiplication. If we are saying if it is a fixed frame we say pre-multiply, and mobile frame we say post-multiply, right? Why that has come. After that we would be seeing what are these two. This is what the flow of this particular lecture. Let us go begin. So we know like the comment on compound rotation at the end of the class, what I mentioned in the sense, you can see that if it is a mobile frame to be rotated by an angle of kth unit vector of the fixed frame, then you have to pre-multiply. Whereas if the you can say rotated by theta angle about the kth unit vector of the mobile frame, then it is post multiply, right? So these are the two things which we were discussed. So I'll give little more insight on that. Then we will move to the global XYZ and as well as ZYX Euler angles. Okay. So we'll see that. For that I'm taking one of the simple example. So in the sense I am taking one of the standard frame A, where that would be associated with the you can say Cartesian coordinate frame, where the unit vectors are XA cap, YA cap and ZA cap. Now I am actually like seeing that there is one frame, body frame is already you can say located in that plane, or you can say in that space, and you can see that that is actually like not directly aligned with the A frame in the sense, so A and B are actually like rotated apart. But if you are closely looking at this, you can see that this ZB and ZA are parallel. If you are closely look at, if you are rotate ZA 90 degree, you can say 90 degree, then you can see that this is what going to get. So before going to see this positive rotation, negative rotation, I would be giving one, you can say another aspect. In this course, throughout we would be using right hand rule in the sense, so this is associated with the x-axis. So thumb finger is associated with the x-axis, and finger is actually like associated y, and middle finger is associated with the z-axis. So wherever we are actually fixing, this is what one of the you can say standard notation we are going to use. Further, for the positive rotation, again we are going to use the right hand rule. So you have to fix, or you have to align the direction of the axis this way, and how the fingers are coming out of this, you can say palm, that is what the positive rotation. In the sense, you can see that the right, you can see this is what your z axis, and we are actually like putting your finger on this and how it is coming out. So in the sense, it is actually like coming out of this. So in the sense, we are actually like rotate 90 degree, this XA will go to XB and YA become YAB, right? So that is what we are actually like seeing. So if that is the case, you can see that what we know, the rotation matrix is projection of the unit vector of B frame vectors on the A frame. So in the sense, the XB vector projected on A frame. So that is actually like you can see parallel to YA, that too like same direction. So in the sense, so other two projections are 0, in the sense the x-axis projection and z-axis projections are 0. That's what you can see. So similarly, YB frame, or you can say YB vector projected on A frame, you can see this is parallel to XA, but it is actually like opposite direction of XA cap. So that's why you can see it is -1 and other two are zeros. So similar sense you can see. So now this is what the rotation matrix. But this is not the discussion what we are bounded to do here. What the discussion here we are actually like bounded to do, if we are rotating with the fixed frame and if we are rotating with moving frame. So what would be the case? So here I said it is a pre-multiply and here we said post-multiply. How that has come. So that is what our interest. So for that what I am taking the same you can say B frame I am taking further, and I am actually like rotating that frame with respect to one of the fixed frame axis. So here we are actually like taking as YA cap as the fixed frame axis, and you can see this is what the case. So now the you can say angle is actually like coming inward, in the sense the YB can actually like come towards the you can say screen. So in the sense here actually like I take for a standard understanding, or you can say simple understanding, I am taking 90 degree. So now what will be the frame arrangement now? So since the YA frame YA axis is actually like aligned with the XB you can say axis, in the sense if I rotate 90 degree what would come? So this YB cap become like this and ZB cap will be like this, and this is what XB cap, right? So this is what going to happen if I do this rotation. So what will happen that? So this is what happening, right? So now I am putting that into a new you can say frame just for understanding. So what we have done here, the operation is actually like with the fixed frame axis. Okay, so we have rotated the frame. So now what would be that case? What would be the rotation matrix? The rotation matrix, this we will come back. The rotation matrix is this. So here we have rotated about y-axis 90 degree. So in the sense you can know like what would be the case. So this is what the case. So now you substitute this and you can see that this becomes 0, this become 1, this is become -1 and this becomes 0, right? So this is what we got it. Okay, but you can see here, already we got, I'll just show, already we know like this we projected on A frame. So you can see that this XC unit vector projected on A frame, that is parallel to YA. So that is what happening here, and YC is actually like parallel to Z, that is what happening, and ZC is actually like parallel to X. So this is what you are you call rotation matrix of C with respect to A. But what we have done initially we know one rotation matrix of you can say B with respect to A, then we have rotated with respect to the fixed frame, that is what we got it. Now I told like if we are actually like rotating with respect to fixed frame, then you have to actually like pre-multiply, right? We'll just check that. So if I actually like pre-multiply this with this, so now I am actually like putting that. Okay, so this is in the sense I am saying that, so RBA I know, now I am actually like pre-multiply this RBA Y 90 degree. Okay. So then what will happen? So I am actually like doing it. Okay, now you actually like multiply this. So what will happen? This is actually like going to be 0, and this vector this row and this you can see like what happening, this is also 0, and this 2 here you can see like, so this third term is there, so 1, and second row and first column, so this would be 1, and second row and second column it is actually like 0, second row third column also 0, third row first column is actually like 0, third row second column -1 to -1 plus 1, and third row third column is 0, right? You can see that we got it what we know already as you can say rotation matrix of C with respect to A. So that's why I said we have to actually like pre-multiply. Now you got a clarity, right? So now this is what we have done as a pre-multiply. Whereas you can see that the B with respect to B frame, which is actually like what it is equivalent. So we have rotated 90 degree with respect to XB frame, right? XB axis. So in the sense if I rotate this, so what will happen? So this is what the case. So you know already X axis. So this is X axis rotation. So this is cos 90 and this is minus sin 90. and this is sine 90 and cos 90, and this is 0. So now if I substitute, this is what going to come. So this is 1 and this is minus 1. So now if I actually like do this post multiplication, definitely this won't come. So what I can do, then I can actually like multiply this with respect to you can say post multiplication. So the pre multiplication won't come, the post multiplication, if I multiply with this, so I will get this. So in the sense, you can see that if you are doing the mobile frame rotation, then you post multiply. If you are doing a fixed frame rotation, you pre multiply. Just to give that idea, so I have given this. So this already you know, right? It is based on the transformation matrix. You know, like, so you have 3 frames and you know the information of this and this, and you want this, you just post to multiply this, right? In the sense, you are going here and reaching here, right? So that is what the idea here. And in the other case, you are actually like from here itself, you are trying to rotate back. So that's why it is actually like pre multiplication and here post multiplication. Okay, you can cross check this with respect to the multiplication and all. So you will get this matrix if you are actually like post multiply here. So with respect to this, you actually like pre multiply, then only you will get this, right? So this is what the idea. So now you got a clarity why we are doing a pre multiplication and post multiplication, right? So now with that we will move forward. So now you got a clarity what we are actually like interested. So now we'll come back to the global XYZ fixed angle. So for that, what I'm actually taking, I'm taking 2 frames. So A frame and B frame. So you can see that the B frame is our interest. So in the sense, what I wanted rotation matrix of B with respect to A. This is what I wanted. But this is not straightforward because you can see that it is having a composite rotation or compound rotation. So what I can do one simple step. I can go with a global XYZ fixed angle. So what I'm doing is actually like I'm taking forward in order to get this. So what I'm actually like doing, I'm going to do 3 operations. So right now you actually like forget about the B frame. Right now you can see like how we are moving forward. So in the sense, I'm taking this frame, A frame, and I'm taking X axis as the reference, in the sense rotation reference. I'm rotating gamma angle. So here I'm taking gamma as 90 degree for giving a simplicity, or you can say ease of understanding. So now if I actually take the XA axis and rotate 90 degree, what happened? This would actually like rotate here, and this will go here and this will go here, right? So what I will get a new coordinate. I'm going to call that as a B1 frame. So here you don't see the distance apart. Just to give a clarity, I'm just putting in a distance apart. So now what I am calling, that is a new coordinate frame B1. So in that sense, the unit vector also X1, Y1 and Z1. So what we have done with respect to this, and we have done this operation. In the sense, with respect to XA, which is a fixed x-axis, in this case it is actually like fixed axis or mobile axis, both are same because this is the only frame. So in the sense, I have taken a fixed axis, I rotated 90 degree with respect to x-axis. So this is what I got a new frame. So what operation I have done, so x-axis and gamma angle, right? So this is what I have done. So now what I can see here, so this is what I have done. So now rotation matrix of 1 with respect to A, I can write with you can say x-axis rotation and the gamma angle. So here the gamma is 90 degree. Okay. So now I'm trying to do second operation. The second operation, what? This is global fixed angle, right? So then what would be the second axis rotation? So I have to take this YA as the fixed axis. So with respect to, I am actually like rotating. So for that, I am actually like bringing the Y axis here. So and I am rotating. Now you can see that it is coming out of this screen. So the beta angle I am rotating. So now what operation I have done? I am actually like taking a fixed axis and rotating with respect to that fixed axis the B1 frame. So now the B1 frame, you can see that the X1 axis goes to here and Y1 axis comes to here. So Z1 axis is parallel to YA, so that would be again retained. So now I will get a new coordinate frame which is I call B2. Okay. So whatever the unit vector I am calling X2, Y2, Z2. Okay. So now what operation I have done? I have done so rotation matrix of you can say 2 with respect to 1 about Y axis I have done. The angle is beta, right? So this is what I have done, right? So this is what I have done. So now the third one is actually like as per here the z axis rotation. So I am trying to do that. So for that what I am taking the so z a here, and I am going to rotate so 90 degree or whatever you call alpha angle. So that is what I am actually like doing it. So now if I do that, what happened? So the z2 and y2 will actually like come here. So now I will get a new coordinate. That coordinate you can see that this is same as your B frame, right? So that is what we have done. So now you can see that in order to get this, whatever operation we have done Rx gamma, then Ry beta, and Rz alpha, right? So these are the three operations we have done, but here what we have done, it is all with respect to the fixed axis. So in the sense of what we know, the fixed axis, in the sense you have to actually like pre-multiply, okay. So this is what your rotation matrix. So that is what we have actually like done. So whatever that angle comes, that is what we call roll pitch angle or Winkle angle. That is what we have seen. This is the third operation we have done. So now if you want to actually like see the rotation matrix of B with respect to A with all the transformation, so you can see that the first we have done this, so then we have done this, finally we have done this, right? So as per what we have used here, we have used rotated with respect to fixed axis or fixed frame, in the sense we are actually like pre-multiplying. This is what you are actually like going to call the global XYZ composite rotation. So now if you are actually like using that into a you can say multiplication factor, and this is what the case, and you multiply the individual matrix, rotation matrix, and you will get this is what the global you can say composite or compound rotation matrix. So now this matrix is equivalent to what? So equivalent to something like a general matrix. So that is I am writing as R11 to R33. But if I know this, okay, and I want to find out alpha, beta, gamma, what I can do, I can actually see there is a transcendental equation, there is a 9 you can say equation, in that only 3 independent variables are there. Then I can see here straightforward, I can see here the sine alpha, cos alpha and all there, and cos beta, sin beta and all there. I can actually like start with beta. So I can take these three terms. I actually like take minus of R31. So what I will get, it would be equivalent to sin beta, and I actually like square 2 1 squared plus R11 squared. What I will get, so sin alpha squared, cos alpha squared, sin beta, sorry, cos beta squared would be there. If I take cos beta squared as common, and this would become 1, right? And if I take a square root of this, what happened, that become actually like cos beta, right? So now I take sin beta divided by cos beta, what I will get, it is a tan beta, right? So now from that I can take, so tan inverse of, you can see this sin beta divided by cos beta, I will get this equation. But what is sin beta, which is actually like minus R31, and what is actually like cos beta, which is actually like function of the square root, right? So from this I can get, and you know like tan inverse is actually like quadrant dependent, so we are using a 2 argument tan inverse, in the sense arctan 2 argument function we are using. In the sense you can see the beta, we can get it like this. So once you know beta, what you want alpha, you can see this R you can see 2 1 and 1 1. So R21 divided by cos beta, what it will be, that is a sin alpha. So R11 divided by cos beta would be as cos alpha. If I take arc tan 2 function, that would be alpha. The similar sense I can go here, you can see that if I divide by cos beta of these two, so what I will get, this would be sin gamma and this would be cos gamma. So then I can actually like use it. So like that I can get the solution, and you know like the beta can be 90 degree, then you can actually like use this different way, because so cos beta is actually like 0, then it would be indefined, or you can say undefined, right? So for that we will use some other you can say relation. That's what we are doing it. But in this particular class, that is not our interest. Our interest is actually like how you can write the rotation matrix in the you can say global XYZ fixed angle. So now this is what the rotation matrix. That rotation matrix is component of 9 terms, and these 9 terms are actually like depend on 3, you can say, independent variable, which is what we call alpha, beta, gamma. So this alpha, beta, gamma is what you call roll, pitch, yaw, angle. Similar sense, we will go forward where we come back with Z, Y, X, Euler angle, or simply we call Cardan and Bryant angle. For that, I am taking the same, you can say, A and B frame, but I am doing operation with respect to movable, or you can say moving frame. You can see first operation what I am doing it, since it is Z, Y, X notation, I am first rotate, you can say, ZA axis about, you can say Z axis I am rotating for psi angle. So now what happened, this become here and this goes here, right? So now I will get a new coordinate system. That coordinate system I call beta 1. Okay, so what operation I have done? I have done simple Z axis rotation. So now the rotation angle, or you can say rotation matrix of 1 with respect to A, I can write as simple rotation matrix with respect to Z axis, right? So now the second one is, it's a Y axis, but not this Y axis. Now this is supposed to be this Y axis, right? Because it is a moving or movable frame, or you can say a body frame rotation. So in that sense, I am actually like taking that as Y1. So Y1 as my frame of reference, in the sense rotation reference, I am rotating a theta angle. So now what happened, this Z1 comes here and X1 comes here, right? So now I move that way. So now I will get another coordinate system, which is I call B2. The B1 to B2, what was happened? So it is actually like RY theta angle, right? But it is actually like rotated with respect to, you call mobile frame, that is right. So now this is what you got it. So now we'll move forward. So what move forward? So you can see like this is I have done. Now I am actually like taking the last rotation, which is about X axis, not this axis, this axis. So now I am taking here, this is a thing, and I am actually like rotating. Okay, so now I am actually like seeing that this is the positive rotation. I am taking a phi angle and rotating. Now what happened, the Z2 comes here, okay, and Y2 come here. So this is what the same as here. Now the new coordinate frame is coming, that is same as B. So now this is what here, what transformation or what rotation we have done. We have taken X axis rotation with mobile frame, that angle called phi. Okay, so now you can see 2 to B, which is actually like simply a X axis rotation. Okay, so this way actually like you can do it. So now what we have seen in the first slide, if it is anything which is what you call with respect to mobile frame, you have to post multiply, in the sense you are going one to another, one to like this you are going. So in the sense you have to actually like post multiply. Here 3 operations we have done, so we are actually like post multiplying this. Okay, so now what you are getting individual matrix, you find it and then you get it. It is actually like the same as in the last sense. Only thing, instead of alpha, beta, gamma, it is actually psi, theta and phi, and you can use the same way, you will get the solution. Okay, so this is what the case, what we wanted to know, the composite or compound rotations. So last class itself I gave introduction, but I want to give a little more detail. So this is what the case. But why this particular compound rotation is important? Because the body in space that would be oriented in 3 axes, so that we need to represent, for representing we are using a rotation matrix, but the rotation matrix is consists of 9 terms. These 9 terms, if we are using these you call angle representation, you can actually like bring back with 3 independent variable. That is what our interest. But you can see one difficulty here is this compound rotation is not straightforward, right? Even you actually like give a wrong interpretation. Instead of pre-multiply, you are using post-multiply. One frame you are actually like rotating with respect to fixed, so other frame you are rotating with respect to mobile frame. You have a lots of confusion, right? So in order to avoid this and in order to make simplicity, we are seeing some you call representation. So this is one aspect. Second thing is, you see any body in 3-dimensional space, you need 3 positional variable and 3 orientation variable. In the sense you have n body, you have 6 into n number of variable to describe the system, right? This is what the you can say truth. So if can we actually like simplify this, or can we actually like modify this? So for that, two popular approaches have come. One is what we call transformation matrix approach. In that, one of the specific approach we are going to focus is, so two popular researchers have done, Danavit and Hartenberg. So they have given DH representation, that is one thing. So the other one is actually like based on the screw algebra, so which is we call screw transformation matrix or screw transformation. So, and in this course, in the serial manipulator, we are very convenient or comfortable with a simple, you call transformation method, or we call simple Danavit-Hartenberg method. So here we are going to bring some of the parameter, what we call kinematic parameter, because we are going to describe the kinematic aspect. So these parameters, what we call kinematic parameter. In general sense, the kinematic parameters are 6. So which are 3 positional variable and 3 orientational variable. So we are trying to modify that. That is what our interest. In the next class, we are going to see that. That is what the you can say important core aspect of this serial manipulator course. Okay. So with that, I am actually like ending this. So although I have given very simple idea behind here, so you can go back the slides and you can actually like see this video and come back with me if you have any, you can say, queries. But the idea here is very straightforward. So you have, one is actually like a fixed frame rotations, then you have to pre-multiply. The other one is actually like rotating with respect to body or moving frame, then you have to post multiply. This is the aspect. So based on that, we have seen that there are 4 common conventions are there. In that, 2 of them are very popular. One is we call Winkle angle or fixed or global XYZ, or simply we call RPY angle. The other one is we call mobile frame rotations, we call Euler angles in general. In that, one of the specific notation we call ZYX, which is we call Cardan or Bryant angles. So these are the things we are actually like focused, and I hope you got clarity on this. In fact, this is what I covered in the last lecture. I want to give little more emphasis on this. So now you got, I hope, little upgradation on this. And I just want to give a small insight here. I have seen in the self-assessment, still few of you are having a still concern on the kinematic aspect. I told already, robot kinematics is not only study of motion, it is one more step further, which is nothing but mapping between 2 coordinate frames, or you can say 2 different spaces. So the robot kinematics in serial manipulator is very straightforward, where you have your configuration, which is we call in manipulator, we can say simply joint arrangement, or in the sense how your link arranged with respect to joint. In the sense the joint variables are actually like having a set that we call configuration space. So the other one is where you have the operating end, or you call task end. So the task end also associated with the variable. In the geometrical model, this is associated with your Cartesian coordinate. In the sense x, y, z, alpha, beta, gamma are the 6 parameters which are involved. We call task space variable or operational space variable. Whereas the configuration space variable, in the sense theta 1 to theta n, which is what you call configuration space variable. Now, the robot kinematics is very straightforward. If you know the configuration space variable and you are trying to find out what is your operational space variable, in the sense you know theta 1 to theta n or theta 1 to dn, you know what would be your end effector position and orientation. This is what you call forward kinematics. Very simple example, you take n number of body and you actually like assign with the constraint whatever the angle given, and see what is your end effector position or what is your operating end. This is what you call assembly mode or forward kinematics. Whereas the other one is, I want this particular, you call position and orientation. Can I actually like arrange my body in such a way that I can reach this? In the sense, I know x, y, z, alpha, beta, gamma. I want to find out what is theta 1 to theta n or theta 1 to theta m and d1 to dn. Okay. So that is what my interest, in the sense I want to know what would be my joint space variable or what would be my configuration space variable. This is what we call inverse kinematics. And still, if you are not clear, you please come back to the live lecture and bring your insight where you are actually like thinking wrong or where conceptually you are wrong, that we can discuss and then we move forward. So with that, this particular lecture is actually like closed here, and we'll see in the afternoon lecture where we have a tutorial session we'll do little more detail on this, you can say transformation matrix, forward kinematics and the compound rotation. With that, I'm ending here. Thank you. See you then. Bye bye.